Hello and welcome back. Today we're going to wrap up Chapter 3, looking at exponential growth and logarithmic models. Now the primary models we're going to focus on are the exponential growth and decay. All right, we've been practicing those a lot. And then we'll also consider a Gaussian model, which is a bell curve, and logarithmic models, natural log and common log, and also, which I really like, the logistic growth model. The logistic growth model is really important for population studies, and you can tell that we have a horizontal asymptote here, above and below max and min, to restrict those populations. All right, so these two models, the logarithmic and the natural logs, they're not too different from what we've been covering so far. All right, let's look at the first example. So here we have a population of fruit flies, and it says that on day 2, there are 100 fruit flies. And on day 4, there are 300. So we can see that it's growing. And we want to calculate approximately how many flies there will be after 5 days. So considering an exponential growth model, we're going to use the general equation y equals a times e to the bx. Now we have these 2 points, 2 100 and 4 300. So we can write 2 equations and then solve for the 2 variables b and a. So let's fill this in. So this will equal 100 equals a times e to the 2b. And this equation would be 300 equals a times e to, what would that be, 4b. Now it's up to you how you want to solve these, all right? But you want to isolate one variable, and to me it's easier to isolate a. So I'm going to write this as a equals 100 over e to the 2b, and a equals 300 over e to the 4b. Now we set those two equal to each other. So we have 100 over e to the 2b, and then we'll have 300 over e to the 4b. So this just takes some cross multiplying, but we'll eventually get e to the 2b equals 3, because 300 divided by 100 is just 3. Now at this point, we want to make sure we use a natural log and take the natural log of both sides. So we'll get 2b equals the natural log of 3, and b equals natural log of 3 over 2. Now we have one variable and we just have to solve for the other. So I'm going to plug this in. Either equation is fine. I'll use the first one. So 100 equals a to the times e to the 2 times natural log of 3 over 2. Well, that's going to simplify. So 100 equals a times e to the natural log of 3. We can also simplify this. So we'll have, that's just going to be 3a, and divide both sides by 3, so a equals 100 over 3. So when I write the equation, we'll have y equals a, which is 100 over 3, and then that'll be times e, and then it was x times b, or b times x. So I'll have x natural log of 3 over 2. And now we want to figure out how many approximate flies there'll be after 5 days. So we'll plug in 5, where we see x. So that's 5 natural log of 3 over 2. And when I put that in the calculator, I want to make sure I round to the nearest fly. So that'll be about 519 fruit flies or flies. All right, so solving for that, we had to write 2 equations and then solve for that system. All right, let's go to the next example. So for this one, I think this is very interesting. It's using carbon dating. So when we actually consider and try to determine how old a fossil is, we're comparing the ratios of the carbon-14, which is radioactive, and the non-radioactive carbon-12. So we're going to use this equation here knowing that the half-life of carbon-14 is about 5,700 years. So when we give the ratio of the carbon-14 to the carbon-12, that's going to help us determine how old a fossil is. So if I'm given that a fossil has a ratio of carbon-14 to carbon-12 as 1 over 10 to the 13th, well, I can say, well, that's going to equal R, and it could essentially set these two equal. So we have e to the negative t over 8,223 over 10 to the 12th. Well, that was my formula, is going to now equal 1 over 10 to the 13th. And here we can cross multiply. So we'll have e to the negative, or just multiply by 10 to the 12th, and we'll have e to the negative t divided by 8,223, and I'll just leave that as 1/10 or 0.1. All right, so from here, we want to make sure we get rid of the e and simplify that exponent. So we're going to take the natural log of both sides. So I'll have negative t over 8,223 will equal the natural log of 1/10. And so if I just multiply both sides by negative 8,223, we can get an approximate value for that, or age for that fossil. And using a calculator, we can see that that's approximately 18,934 years. Pretty old. All right, for our last example, we're going to look at earthquakes. And on the Richter scale, the magnitude can be determined with the given intensity I. And the minimum intensity for this comparison, I sub 0, is going to equal 1. So we know that R would just be the log of I. So if we're given that the Richter scale, or an earthquake in northern Sumatra, has an intensity of 9.0, then we can simply set this equal to each other. So we'll just say 9.0, or 9, equals the log of I. And from here, we have a log on one side, so we can rewrite this in exponential form as 10 to the 9th, which will be 1 billion. Put all those zeros there. All right. Now let's look at an earthquake in southeastern Alaska. So we'll set this equation 6.8 equals log of I, and we can rewrite that in exponential form. So the intensity will just be 10 to the 6.8, which will be, let's put this in approximate, because I will have to round this. And that's 6,309,573, and I'll just round it to 4.5. Well, I hope this lesson was helpful, and I'll see you all in class.